going to use some real elements, to actually show you beta decay again. So we have carbon 14. It is going to decay into, well, this is going to be beta minus decay, which is the one that's the most common, okay? And it's talked about in the book more. This just happened to come up in an exam one year, so I'm making sure I cover it. So for beta minus, remember what happens. A neutron in the nucleus turns into a proton plus an electron, okay? That means your number of protons is going to go up by 1, and you have an electron. So if the number of protons goes up, it becomes a new element, and that new element is nitrogen. Now, the number of protons goes up, but the number of neutrons goes down, so the sum of protons and neutrons doesn't change. From the point of view of charge, an electron has a charge of -1, and it has a mass of pretty much 0, okay? It's not 0, but compared to the protons and the neutrons, it is. So when you add 0 and 14, you get the same sum, left and right, in terms of masses, atomic masses. Now, in terms of this number, when we look at it in terms of charge, the charge on an electron is -1, the charge on 7 protons is +7, and the charge on 6 protons is +6. So the charge within the nucleus is also preserved, okay? Now, we have, obviously the charges of these atoms, as you step out and look outside the nucleus, because you have electrons and so on, then we do have a neutral atoms. There's 7 electrons flying around the nucleus as well. But just in terms of the reaction that happens, it makes sense that a charge of +6 here is still a charge of +6 here. Now, again, the masses of these two summed together, and their energy, the equivalent energy calculated using E = mc², is less than the mass of this. And we knew this, and scientists knew this, and they said, yes, that excess energy is in the form of kinetic energy of the, mostly the beta particle, okay? But then when they added it up, they worked out the kinetic energy of the beta particle, they worked out the sum of the energies again on this side, and the sum of the energies on this side, and again, there was still missing energy on this side. This side had more energy. So that's when Wolfgang Pauli proposed the existence of some other particle that was carrying away more of the energy, okay? Its kinetic energy. So that particle is the neutrino, or in this case it's the antineutrino, in the case of beta minus decay with an electron, okay? And the neutrino again was predicted well before it was discovered. And again, that's interesting because that happens in science a lot, where the maths actually predicts the existence of something before it's actually discovered or detected. But that does help to point scientists in the direction of looking for something that is there, must be there. Otherwise the energy couldn't be explained, or the law of conservation of energy wasn't being applied here. So eventually they discovered the neutrino and the antineutrino. Now, just on a quick one on, if we now look at beta plus decay, you have carbon 14-6. What happens in beta plus decay is that a proton turns itself into a neutron and a positron. Okay, so again, now you would have carbon 14-6. One of its protons is turned into a neutron, so it drops in atomic number by 1, which makes it a new element, boron. And yet its atomic mass stays the same because you have the same number of protons and neutrons, because one proton has turned into a neutron, but you still have the same overall number of the two. You get your positron, and the difference in energies between the masses was assumed. This was your kinetic energy of your positron, mostly. So now, again, when they added up, when looking at the charge first, this is a charge of +1, sorry. So +1 and 5 gives you 6. So again, from the point of view of the nucleus, you had a +6, and you have still got this +6 coming out the other side. And you have your kinetic energy here, but when they worked out the kinetic energy of the positron plus the energy of the two masses, added all that energy together on this side, all the energy on this side, there wasn't a balance. This was still too low, So again, that's where your neutrino, and actually, sorry, your neutrino has a charge of 0 and pretty much a mass of 0. Okay, so it doesn't affect the balance of the equation. And that should explain really the two types of beta decay. And as you can see here, really, beta decay is usually followed by something else because there is a lot of excess mass in the nucleus now. Okay,